Our next topic for today is a normal approximation to a binomial distribution. This is the historical origin of the normal distribution, actually. I didn't look it up. I think it was Gauss who discovered this, and that's why normal distributions are sometimes called Gaussians. That's my assumption, at least. Gauss lived a couple hundred years ago, so the normal distribution is a couple hundred years old. Why would you need to approximate the binomial distribution? Well, remember the PDF for a binomial distribution involves n choose x. What if you're flipping a coin 100 times, so n is 100, and you're wondering what the probability is that you get 45 heads, so x is 45? You'd have to compute 100 choose 45. 100 factorial divided by 45 factorial times 55 factorial. 200 years ago, no technology to do that, even 100 years ago. So they needed some other method to approximate the probability. And Gauss, I think, came up with a normal curve to do it. There's a theorem, though as this is stated, it's not really a theorem in the usual sense of the word, because it's too imprecise. Our book is okay with kind of imprecise theorems and calling them theorems. Theorems should be precise. You should be able to say exactly what you mean so you can prove them. This is kind of hand-wavy, like what does large mean and what does approximately mean? So it's not really stated as a theorem in the usual sense. Let X be BNP. B stands for binomial. Chapter 3, right? Binomial random variables are discrete, counting the number of successes in n trials when the probability of success P stays constant from trial to trial, like flipping a coin or rolling a die or shooting a free throw. And each trial is independent of what happened previously. All those assumptions were important. Then when n is large, how large is large? Don't worry about it. A moment at least. That x, the random variable, is approximated by a normal distribution. Think about our notation here. With mean, this first number must be the mean, n times p. Oh yeah, the n times p, that's the mean of a binomial, right? 40% free throw shooter, Dr. Kinney. I attempt 20 free throws, n is 20. My probability of success is 0.4. I'm probably going to make close to 8 free throws, 20 times 0.4. That's the mean. I don't know if you remember, the variance is what you see here. N times P times Q. N times P times 1 minus P. We did talk about that at least one day. Yeah, N times P times Q. And then the standard deviation would be the square root of that. This is a little weird in another way. Anybody have a feeling for what I'm talking about? How else is this weird besides the words large and approximately in a theorem? X is discrete, binomial. Normals are continuous. Huh? How can X be approximately continuous if it's discrete? Well, we'll talk about that briefly here in a minute. And it's related to this note. When using this fact, we have to make something called use of the half-unit correction or correction for continuity to assure as much accuracy as possible. And this picture is a pseudo-justification for that. What we have here is a picture of two things. A histogram, specialized kind of bar chart, giving us probabilities for a binomial. Looks like probably n is 10 and p is 0.5. It's got a highest value near 0.5. That's where that highest bar is here. Actually, it doesn't look perfectly symmetric, so maybe p is not exactly 0.5, but close enough. And then you see what looks like a normal curve. Yeah. We're going to approximate the area of the bars that give you probabilities for a binomial with areas under the normal curve. And what's shaded here, that red area under the normal curve is the area under the normal curve from 7.5 onward. It is hopefully well approximating the area of these three bars added together. But wait a minute, we've never computed area probabilities for discrete random variables as areas, have we? We've always just plugged numbers into PMFs and added them up. Remember, the true graph of the binomial, in the way we talked about it back in chapter 3, say when n is 10 and p is 0.5, the true graph for a discrete random variable is a piecewise function. It's discontinuous. It would only be positive at starting at 0, then 1, then 2, then 3, etc. And it would be 0 otherwise. Remember me emphasizing that? And there's no areas under dots like that. Those lines don't have any area. Those lines, those vertical distances represent the true probabilities. Why could we think about it as areas? Well, it's because each of these bars has a width of 1. That's why. So the height of the bar is the same as the area of the bar, because the width is 1. Of course, units for length and units for area are different. Don't worry about it. The numerical value of the area is the same as the numerical value of the height if the base has a width of 1, which these bars do. So we can interpret probabilities for discrete random variables as areas if we want, if we're careful. And yeah, so what we're after here in this example, this visual example, is the probability that x is 8, 9, or 10 greater than or equal to 8. X is binomial with parameters 10 and 0.5. What is the probability that x is greater than or equal to 8? To find it most precisely, we'd want to use our technology. We'd want to write this as 1 minus the probability that x is less than 8 with the complement rule. And then the fact that x is discrete means we want to write that as 1 minus the probability that x is less than or equal to 7. And we'd want to use a binomial CDF with input 7. Go to binomial CDF. N is 10, P is 0.5, X value is 7, not 8. If that were a strict greater than, then I'd have a less than or equal to 8 there, and we'd use 8. But it's a greater than or equal to there, so this has to be a strict less than, and because X is discrete, I have to convert it to a 7 with a less than or equal to. One minus that, oops. 1 minus the previous answer is about 0.055. 0.0547, let's say. If we used the normal curve in the way you see in the picture, how close would we get? Well, again, we have to use this half-unit correction idea. Don't find the area under the normal curve to the right of 8. Find it to the right of 7.5. Because we're trying to estimate the area of these three bars together, and these bars are centered on the whole number values. They're centered on them. So this bar, for example, its left endpoint is on 7.5 and its right endpoint is on 8.5. That's called the half-unit correction for the continuity of the normal curve. If I say let y, excuse me, let y be normal with mean n times p and variance n times p times q, since P is 0.5, Q is 0.5. So that's normal with mean 5 and variance 2.5. That's sigma squared. Well, okay, let's just call it variance. And so the standard deviation is square root of 2.5. That's going to be approximately 1.58114, say. The idea is that I should be able to use y and its distribution to approximate probabilities for x. But again, I have to use that half unit correction. The probability that x is greater than or equal to 8 should be approximately the probability that y is greater than or equal to 7.5. How do I need to know I need to use 7.5 as opposed to 8.5? You look at the picture. You draw the picture. That's how. As you can see in that picture, we're trying to estimate the areas of the bars, including this one, the rectangles, and we're using the appropriate area under the normal curve. I got to start at 7.5 since the left side of that rectangle is at 7.5. Got to do that. Actually, when we teach this to the statistical analysis students, we don't talk about the half unit correction. We just say it's good enough if they use an 8 here, but you guys can handle it here. And that's going to be the approximately the probability that z, convert to z, standard normal. Or yeah, I mean, you can use your calculator without doing this, but I want you to be able to do this. And I do want you to do this not only for today's homework, but for the one due next Tuesday. Standardize, subtract the mean, which is 5, divided by the standard deviation, not the variance, standard deviation. That's standardization. (7.5 minus 5 is 2.5. This is approximately the probability that z is greater than or equal to, oh, how about that? That's quite a coincidence. That's just a coincidence. Taking 2.5 divided by its square root, it's going to be its square root, right? You know that. Take a positive number and divide by its square root, you get the square root. Okay, that's just a coincidence of the fact that of how these numbers worked out. If I had done a different example with a different number there and a different number there, it wouldn't have happened. So I happen to get 1.58114 here still, though if I'm going to use a table, the normal table, I'd want to put 1.58, round it, say. They're all still approximations. Could use the normal table. Let's just, to save time, let's use technology here. Let's use a normal CDF value. Standard normal, which it's set to by default. I already did the 1 minus. Get about 0.0571. Is that the right answer? It's not as precise as the true correct answer. This is better. 0.0547, but that's not too terribly far off. And n is not even that big. And it's just 10 here. And we got reasonably close. 0.0547 compared to 0.0571. That's the better answer up there. This is the answer you get with the normal approximation. The normal approximations get better as n gets bigger, as long as p is not too close to 0 or 1. Say that again. The normal approximation gets better as the number of trials n gets bigger, as long as p is not too close to 0 or too close to 1. When p gets too close to 0 or too close to 1, then the binomial distribution tends to be less normal, even when n is large. Very rough statements there, okay? So I'm gonna give you a little practice with this for the assignment due next Tuesday as well.